This is chapter 5 in CCNA1, and this is the first part about the Ethernet protocol. The Ethernet protocol is one of the most widely used LAN technology. Well, it is the most used LAN technology. I think about 99% of all local area networks run on Ethernet. It operates on both the data link layer and on the physical layer, and we have a whole family of technologies that defines these different technologies and protocols. They are all in the IEEE, and they all start with 802, and it's 802.2 and 802.3 standards. It supports a lot of bandwidth from 10 megabits and up until 100 gigabits as the highest. The Ethernet standards define on layer 2, but we separate them into two sublayers, the LLC and the MAC Sublayer. We can see here that we have divided the data link layer into two. And in the IEEE standard, the 802.2 defines the LLC layer and the 802.3 defines the MAC layer. The LLC layer handles the communication upwards in the model or in the protocol, typically communicating with the IP protocol on top of that, in layer 3, whereas the MAC layer is the sublayer that takes care of the implementation on the physical layer and the media access control on the data link layer. If we look at them, we have a wide area of different types. On 802.3, we can see that we have different implementations which handles different types of cabling. For instance, we have the 10-base-5, which is the thick yellow cable, the coaxial cable, the yellow one, the oldest one, the thick one, implemented on that. We have the 10-base-2, which is the same but on the thin coax cable. We have 10-base-T, which is 10 megabit Ethernet on twisted pair cabling. We have 100-base-TX, which is 100 megabit on the twisted pair cables. And so we have a lot of different implementations regarding what type of a cable that we are using. 10-base-T, 1000-base-T is 1 gigabit on twisted pair cable. We have 1000-base-ST on different types of fiber cables, 1000-base-LX on another type of fiber cables, so we can see what types of cables that we are operating in. And that is, you can see why we have the LLC link, the link control layer up here, because it doesn't really care about what kind of cables that we are using, because it should only communicate upwards in the protocol. Whereas down here, we need to know what kind of a cable do we have underneath. So the sublayer will take care of the encapsulation. It will take care of setting the different fields in the frame, which is the addressing, the error detection, the frame delimiting, where you can see whether we are stopping or starting to send the frame. Then, so that the MAC layer communicates directly with the physical layer, it will make sure that we can just send whenever we like to send. And this is how it works in Ethernet. We have the media access control called CSMA, which is Carrier Sense Multiple Access, which means that we can just sense if someone else is sending, and if no one else is sending, well, then I can just start sending my data. Multiple access is for, of course, as it says, we have all access to the same network. If no carrier signal is detected, well, then I can just send data. But of course, there could be this occasion where two is listening in on the same time, and then we can have a data collision. And that is the problems we have in these types of networks. Well, today we really don't have the problem, but in the early days of the Ethernet, it was a huge problem that we could have a lot of collisions on the network. Then in Ethernet, we have CSMA combined with CD, which is for collision detection, so that we will actually find out if there is a collision and then we can handle that. Whereas on wireless networks, we kind of like use the same media access control, but here we use collision avoidance instead. So here it is CSMA CA for collision avoidance. But as I said, on a Ethernet, we have collision detection, so that if there is a collision and all the devices connected to the same cable will sense that collision, and then if I know I've just sent something and there is a collision, well, then I know I have been involved with a collision, and then my network interface card will start counting, set a timer, and then when this timer is 0, then I will send again. And then, of course, there could be a collision again, and then it will try to send again. So the whole thing here is to find out if there has been a collision and then handle it. Whereas on a wireless network, we use collision avoidance instead. So here, I need to make sure that the other ones know that now I'm going to send something. So I'll send out a small request to send package before I start sending it. And then the other ones will know, okay, I will not send now because someone else is starting to send. So here we try to avoid the collisions instead of handle them. When we look at the addressing field, we are using the MAC address here, the Media Access Control address, which is the physical address which is printed on all network interface card, which is of course implemented to use Ethernet. Here the address is a 48-bit binary value. The first part of the MAC address, it's the organizationally unique identifier, which means the vendor ID. So here we can see who's been producing the MAC address or the network interface card. And then the other part, the last part of it, the last 24 bits, is just a vendor assigned number, which is basically just a unique number. So altogether, the MAC address must be a unique address on the network. We will see that the MAC address are assigned to all devices on our local area network, and the local area network is always just using the MAC address when it sends something. We can see it if we have been looking at what kind of a MAC address we have. You can see it's typically given in hexadecimal numbers, because all the 48 zeros and 1 will be just confusing for us to look at. So that's why we will keep them in hexadecimal numbers. So each network interface card has its own unique MAC address. If I have 2 different network interface cards in my computer, I will have 2 MAC addresses as well. And we can see here that there were 2 different implementations of Ethernet. The first one, the original Ethernet, is called Ethernet 2, or DICS Ethernet. It was created by Digital, Intel, and Xerox. So their original implementation is called Ethernet 2, and then we have the IEEE802.3 implementation, which is the standard implementation. And you will and you will see that some devices uses 802 version, and the other might use the Ethernet 2 version. It doesn't really matter. They can work together because there isn't really that big difference between them. What we can see the difference here is the length field here in 802.3 is the same as the type field in Ethernet 2. Otherwise, it's and the length of the different fields are the same. Yeah, so we can see the frame size. Here we have a minimum frame size of 64 bits and a maximum of 1518. If we find on our network a frame that is smaller than that, well, then we know that this is something else. Typically it's a collision fragment, or it's also called a runt frame, which is a smaller than minimum frame. We will also see, of course, that if we have something that is larger, then it's called a giant. And then, of course, there's also something that has gone wrong when we have a too large frame. We have made some changes to the Ethernet lately, where we have added 4 extra bytes, which is something that we would need for VLAN tagging. And this is done only on the local area networks, and we can actually do that if we, put it in on all our devices. So this is typically something that the switch will put in to identify which VLAN a packet belongs to. It's called VLAN tagging, or 802.1q. So here you can see the 802.3 field Ethernet frame, where we start with the preamble. It's just something that tells us that now there is something coming. Then we have the start of frame delimiter, which will tell us this is the start. Then we have the destination address, MAC address of 6 bytes, and the source MAC address. Then we have the length field, and then we have the actual data, which is from 46 and up to 1500 in the field here. And then we have the frame check sequence in the end, which is a checksum, which we calculate before we send and we calculate when we receive it, and we see if these two are the same, then we know that nothing has happened to the packet, so no error has occurred here. And that was the first part. Thank you.